Now, continuing on, section 4.3. The table shows the number of new branches in each figure of the pattern below. What is a pattern we can use to complete the table? Represent the relationship using words, an equation, and a graph. So here in figure 1, we have 1, 2, 3 branches. And those branches continue into figure 2 and into figure 3. In figure 2, each set of branches from figure 1 gets their own set. So now each of the 3 from figure 1 have 3 of their own. So now we have 9. 3 branches times 3 new branches. And those same branches are here in the third figure. Now in figure 3, each of those branches have their own set of new branches. So we have 27. All 9 of those times 3 branches for each new branch from figure 2. In 4, it's like each branch here in the yellow from figure 3 gets their own. And I'm not going to draw all these out because they don't all fit, but we get the idea there. So each of our 27 branches in figure 3 in yellow get their own green, which means we multiply 27 by 3 to get to 81. And in figure 5, each of our green branches gets 3 of their own blue branches. So all 81 of our green branches have 3 of their new own. So 81 times 3 gives me 243. To figure out our pattern that we can complete the table, we did it from the picture here. So in words, we could say, this was an answer that I got in one of the classes. The figure number tells us how many times we've gotten new branches, and each set of new branches is 3 times the number of branches in the previous figure. So for example, in figure 5, we've had new branches 5 times. So 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. We can also think about this in terms of the pattern itself. So, for example, we have 3 branches in figure 1, and those 3 are in figure 2, and 3, and 4, and 5. Then in figure 2, we got the orange branches, and those stayed in figure 3, and in figure 4, and in figure 5. And in figure 3, we got the yellows, and those are still there in 4 and in 5. And in figure 4, we got the greens, and those are still there in 5. And in figure 5, we got the blues. So if we look here, the thing that stays the same every time as far as our equation goes, our number of new branches equals, is the 3. The number that's being multiplied times itself. Okay, that's the part that stays the same, our base. The part that changes every time is our number of 3's. So here, 3 was multiplied once. Here, 3 times 3 twice, 3 times 3 3 times, 3 times 3 times 3 times 3, 3 times itself 5 times. And those match my figure numbers here. Those are also my exponent, because that tells me how many times my base was multiplied times itself. So y equals 3 raised to the x power is my equation. Now my graph here. Here I set up my graph. My figure number is my input, that goes on the bottom. And there I just went by 1 since they went up by 1. My new branches goes on the side. Here I needed to go all the way up to 243. And I have 12 spots. So I took 243 divided by 12, and I got approximately 20. So I went by 20s on my scale. Remember, they have to be the same distance between all of them. So if I start by 20s, I have to keep going by 20s. Now, I have for figure 1, I had an output of 3. For figure 2, 9. Figure 3, 27. figure 4, 81, and 5, 243. And if we look here, we cannot connect those because I don't have an in-between number of figures. I guess I could go 0, but I can't go any further to the left. And I could go further to the right. We could add more branches based off more figures. If we look here, because this doesn't go up by the same amount each time, I can't use a straight edge to connect that. That means this is nonlinear. A function can be thought of as a rule that you apply to the input to get the output. We can describe a nonlinear function with words or with an equation, just like with linear functions. So in example 3, we're going to describe a nonlinear function by writing a rule, which means an equation. The ordered pairs 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32 represent a function. What is the rule that represents the function? So the first thing I'm going to do is I'm going to write these as an input-output table. X's are my inputs, and my outputs for each, I have 1, 2, 2, 4, 3, 8, 4, 16, and 5, 32. Now, I'm going to see if I can figure out some kind of a pattern. How we get from one to another, for example. So, I have an output of 2 for figure 1, for point 1, an input of 1. I then go to 4, which I can write as 2 times 2. Then I have 8. And if I look at 8, I can rewrite it in 2's as well. 2 times 4, which is 2 times 2. 16 I can write all the way in terms of 2's as well. And 32 is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. So I can rewrite all of these outputs in terms of 2's, multiples of 2's. So here I have 2 to the first power, I have 2 to the second power, I have 2 to the third power, 2 to the fourth power, 2 to the fifth power. It tells me how many times I was multiplying my base 2, and that's the part that stays the same. So when it comes to my equation, y equals, my base is the part that stayed the same. Okay, it's always a 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Okay, my base is the part that always stayed the same. The part that changes is my variable. And here, I had 1, 2, 3, 4, and 5 2's. Those changed, but if you look, they match. For an input of 1, I had a 1, 2. For an input of 2, I had 2 2's. Input of 3, I had 3 2's. Input of 4, I had 4 2's. Input of 5, I had 5 2's. Which means my exponent matches my input. And here I get 2 to the x power. The part that changes is my variable. And here that matches my input, my x value. Now, what is the rule for the function represented by the ordered pairs 1, 1, 2, 4, 3, 9, 4, 16, and 5, 25? So again, I'm going to rewrite this as an input-output table. If I input 1, I get out 1. If I input 2, I get out 4. If I input 3, I get out 9. Input 4, get out 16. Input 5, get out 25. So here when we starting off with 1 isn't very helpful. There's a lot of different ways we can get to 1. We can multiply by 1. We can take it to powers. So that one's kind of hard to start with. So I'm going to start with the 4. And I can rewrite that 4 as 2 times 2. So if I look, I'm going to try and find a pattern. So can I rewrite 9 in terms of 2's? I can't. So I can rewrite 9 as 3 times 3 though. And in looking for a pattern, we only have 2 things. So it's hard to say for sure we have a pattern, but it looks like maybe it's something times itself. So can we rewrite 16 as something times itself? You bet. 4 times 4. 25 is 5 times 5. And I can rewrite 1 as 1 times 1. So here, I do seem to have a pattern. It looks like my base matches my input value. So the part that changes every time here is my base. And that matches my x value. So my base is x. The part that stays the same every time is that I have 2 1s, 2 2s, 2 3s, 2 4s, 2 5s. So it's squared. Okay, how many times they're being multiplied times each other? That's my exponent. And here it's always 2, so in my equation, I make it always 2. Quick recap here. Just like linear functions, nonlinear functions can be represented using words, tables, sets of ordered pairs, and graphs. A nonlinear function is a function whose graph is not a line or part of a line. And that's all I have for section 4.3.